Hello students, this is Mr. Ezra. In today's video, we are going to talk about how to solve quadratics when you have this special case that there is a difference of two squares. So if you had me in the ninth grade, I probably gave you a quiz or a test or something where I made you memorize a whole bunch of perfect squares. And I suggested that you have them memorized through high school math and into college. And well, here we are again where you have this list of perfect squares that must be memorized because for this method to work, you have to be able to recognize a perfect square when you see it. And it's really not that bad. You probably know 1 through 10. Add 11 to 20 on, and you will be ready to go in almost any case. Also, remember that variables like x squared or x to the fourth or x to the sixth, they must have an even exponent to be a perfect square. So x to the third power is not a perfect square. It has to be an even exponent like 2, 4, 6, 8, 10, etc. As we go through these problems, we're going to have three things that we're going to do. First, we're going to make sure that we have two perfect squares. We're going to look at the left one, we're going to look at the right one, and we're going to ask ourselves, are they perfect squares? Because remember, we have this list memorized. 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, 169, 196, 225, 256, 289, 324, 361, and 400. Wow, it's like I was just reading them off, but I've got them memorized. Pretty much, most of them. Anyway, the second thing that we want to look for is we want to make sure that it has a subtraction sign between the two things, between the two terms. So it must have a minus or a subtraction sign. And then we're just going to take the square root of each term and kind of put it into parentheses to factor it. So how is this going to look like? Is x squared a perfect square? Well, yes, it is. It's x times x, right? Is 16 a perfect square? Yes, it is. It's 4 times 4. So the way that this works is we take the square root of x and we put it first. Sorry, the square root of x squared and we put it first. That's x times x. We take the square root of 16, which is 4 times 4, and we put it at the end. And we're going to use a positive and a negative sign. So both a negative sign and a positive sign. And this is the factor of x squared minus 16. Now, I'm not going to do this every time, but let's talk about why this works. When you multiply x times x, if you're foiling this out, you get x squared. The outside, x times 4 is 4x. The inside, negative 4 times x is negative 4x. And the last times the last is negative 16. And what you'll notice is that positive 4x minus 4x, they cancel each other out, leaving us with just x squared minus 16. Well, that happens every time you have something minus something times something plus something. As long as the first term is the same and the second term is the same, the middle inside and outside of the FOIL are going to cancel each other out. So let's erase that. And that is, in fact, our answer right there. You can circle it up. Let's look at the next one. Is 4 a perfect square? Yes, it's 2 times 2. Is 81 a perfect square? Yes, it's 9 times 9. Now, x squared is a perfect square because it's even exponent. Y squared is a perfect square. It's an even exponent. So let's break this apart. Get my two parentheses going. And the square root of 4x squared is 2x. 2x times 2x is 4x squared. You have to break up the 4 as a square root of 4 and the x squared as the square root of x squared. 81y squared is going to become 9y times 9y. And we must have the negative sign and the positive sign in here. And that is our answer. That's it. Now 50 is not a perfect square. It's not in my list here, and I know it's not a perfect square, but there's something we talked about early on, and that is something called a greatest common factor. If there is something that divides evenly into both parts, you want to divide both parts by that thing and divide out that common factor. Between 50 and 32, the common factor is 2. When I divide 2 out to the front, I get 25x squared minus 16. So by taking out the greatest common factor, now I have a perfect square minus a perfect square. I have my two perfect squares, I have my subtraction, so I'm going to take the square root of each of them. When you take out a greatest common factor, a GCF, it is a factor. It needs to stay at the front of the problem. You just leave it up front before you draw your two parentheses. So the square root of 25x squared is 5x. That goes first. Beginning of the two parentheses. The square root of 16 is 4. That goes at the end of the two parentheses. And then to get this minus here, you're going to have a negative and a positive. So that would be our final answer there. Looking good. All right, finally, you see the asterisks here. Usually your directions are going to say something like factor completely, right? Well, when we factor x to the fourth, the square root of x to the fourth is x squared, because x squared times x squared is x to the fourth. If you had x to the sixth there, the square root of x to the sixth is x to the third, because x to the third times x to the third is x to the sixth. So when we break this apart into our parentheses, and we take the square root of x to the fourth, it's going to be x squared times x squared. The square root of 16 is 4. And we're going to have our minus sign and our plus sign. Now, when you're looking at these, since x to the fourth factored to give us x squared minus 4 and x squared plus 4, since x to the fourth minus 16 gave us those, I want you to look closely at these and notice that x squared minus 4 fits this pattern of two perfect squares having subtraction. So we're going to take the square root of those and break them up even a little bit more. So the square root of x squared is x times x. The square root of 4 is 2 times 2. And then we have a minus and a plus. Now this pattern does not work with the sum of two perfect squares. In fact, we'll talk about that in another video. X squared plus 4 does not break apart, so it is going to stay as x squared plus 4. Remember, for this pattern, you must have subtraction. Well, addition is not subtraction. So this has three factors: x minus 2, x plus 2, and x squared plus 4. Well, that is factoring. I might also ask you to actually solve the equations. We call this finding roots, or finding zeros, or finding solutions. So we're going to find the roots using the difference of two squares. Now, in order to do this, we're going to use that pattern for factoring that we just discussed to factor it completely. We're then going to set each factor equal to 0 and check each solution in the original equation to make sure that we got it right. Coincidentally, we have talked about a strategy in a previous video where we just basically use square roots, and you can do that here too. You can move the constant to the opposite side using addition or subtraction, and then take the square root of both sides. And that's another way to do it. But since we're talking about this pattern of the difference of two squares, that's predominantly what I'm going to use for these problems. So when I factor x squared minus 25, I get x minus 5 times x plus 5. That's factoring completely using this new square root of the first and square root of the second. I then set both of these equal to 0. X minus 5 equal to 0 and x plus 5 equal to 0, and I solve them both, and I get positive 5 and negative 5. Now, it's always a good idea to plug those back in and check them to make sure they work. 5 squared is 25. 25 minus 25 is 0. Negative 5 squared, make sure that if you use your calculator, you put the negative 5 in parentheses. Negative 5 squared is 25. Also, 25 minus 25 is 0. So it works. Easy peasy lemon squeezy. Now, if you were looking at this old method over here, it is perfectly okay for you to use this alternate method that we've talked about before. It's just a different tool in the toolbox that can achieve the same goal. So if you remember, what we would do with this method is we would add 25 to the right side, And then we would take the square root of both sides. All right, take the square root of x squared and the square root of 25, and we would get x equals, and we made sure that we wrote positive or negative square root of 25, which is 5. So that's another way to get the same answer. And then remember, I asked you to list them out because there are 2 solutions to list them out. Either way is fine. In this video, I'm going to stick with the new method. But just remember that the old method works just as well, and you are welcome to use it, unless I specifically say use the difference of 2 squares. Let's look at example 6. In example 6, we have x squared minus 121 equals 0. I should be able to know a perfect square when I see it, and 121 is a perfect square. It's 11 times 11. X squared is a perfect square root of x times x, so I can break this apart to be x minus 11 times x plus 11. That pattern always works. Set these equal to 0. X minus 11 equals 0, and x plus 11 equals 0. To get 2 solutions, add 11, subtract 11, and I get x equals both positive 11 and negative 11. We're going to run through these next few examples as quickly as we can. In number 7, since I don't have a perfect square minus a perfect square, I'm probably not going to waste my time subtracting 81 to the left just so that I can use this special technique. If it's already written as x squared equals 81, I'm just going to take the square root of both sides. I think that would be a little bit quicker for me, and I would just get x equals, and I must remember that it's both it's a positive or negative 9. Because 9 times 9 is 81, and negative 9 times negative 9 is 81. So I've got 2 solutions, negative 9 and positive 9. So in that example, I'm not going to use the new technique because of the way that the question was written. I'm not going to waste my time moving it across. But if you had subtracted 81 to get x squared minus 81 equals 0 and then applied this new technique, that would have been fine. Okay. What do you notice about number 8? Well, they're not perfect squares, are they? But what do you see? Do you see a greatest common factor? Hopefully you see that 3 goes into both of those numbers. So what we want to do is we want to factor out that 3, divide out that 3, leaving us with x squared minus 16. The 3 is still out front. I can now break apart x squared minus 16 because 16 is a perfect square. It's going to be x minus 4 times x plus 4 equals 0. Now, remember, I've been showing you a technique where we're technically going to set x minus 4 equal to 0 and x plus 4 equal to 0. But we can do the opposite of the constant over the coefficient. Here, that will be positive 4 over 1 and negative 4 over 1. That's a little shortcut that you can use rather than writing it out every time. Now, occasionally I have a student that says, what about the 3? That 3 out there, what do I do with it? And the answer is, unless there is a variable that we have factored out as a greatest common factor, when we're solving, when we're finding zeros or roots, we ignore the 3. It's there, it's a factor, but it's not going to be a part of our solution because it doesn't have a variable. We can't change it. It's always going to be a 3. Okay, so we started with a greatest common factor of 3, then we factored using this new technique of the difference of 2 squared, and then we got our 2 solutions. Question number 9, perfect square, 4x squared, perfect square, 49. So I can just go ahead and break this up. The square root of 4x squared is 2x. The square root of 49 is 7. And remember, you have to have both a minus sign and a plus sign for this to work. Now, we'll set both of these equal to 0. And what's going to happen when we set them equal to 0? I know some of you are thinking, well, why don't you just do opposite over coefficient, opposite of the constant over the coefficient? Well, I could. It would be much faster, but I'm going to go ahead and write this out. We first would add 7. That's why we get the opposite of the constant, because we're adding it across, right? And then we get it over the coefficient because we're dividing by the coefficient. We're going to divide by 2 to get 7 over 2. And of course, I think you know what the other one's going to be. It's going to be the opposite of 7 over 2, but we'll go ahead and subtract 7 and then divide by 2 to get negative 7 over 2. So our two answers are 7 over 2 and negative 7 over 2. And our final question, we've got 12x to the third minus 75x equals 0. Well, some of you may be thinking, well, 12's not a perfect square. It's not on that list that you gave me, Mr. Ezra. And that's true, but we always look for a common factor. And here, there is a common factor between 12 and 75. There's something that divides into both of them. We want to find that thing and divide it out. In this case, 12 and 75 are both divisible by 3. And I want you to also notice that there is an x in both parts. X to the third and x. And remember, the greatest common factor when you have a variable is just the smaller of the two. So between x to the third and x is smaller, so we're going to factor out the x. This means when we divide by 3 and by x. So 12 divided by 3 is 4. X to the third divided by x is x squared. Negative 75 divided by 3 is negative 25. X divided by x cancels out. And now, ladies and gentlemen, we have 4x squared minus 25. Perfect square minus perfect square. So we can break it apart. Now remember, the 3x came out to the front. It stays there. But we break this into two parentheses with square root of the beginning, 2x, square root of the end, 5, minus and plus. With quadratics, with x squareds, you should have noticed that we always have two solutions. Well, we don't really start off here with a quadratic. What we start off with here is a cubic, an x to the third power. That means that we should end up with 3 solutions. And since we factored out an x, this first part, 3x, unlike the example above it, where we didn't have an x, here we have an x, we're going to set that 3x equal to 0. Just like we're going to set 2x minus 5 equal to 0 and 2x plus 5 equal to 0. Divide both sides by 3 for that first solution. Well, 0 divided by 3 is 0. So one of our roots, one of our solutions, one of our zeros, remember those words are interchangeable, is 0. For the others, we're going to add 5 and divide by 2, subtract 5 and divide by 2 to get positive 5 over 2 and negative 5 over 2. We've actually 3 solutions here, 0, 5 halves, and negative 5 halves. Remember, when you're listing out your solutions or your zeros, the order that you list them doesn't matter as long as you have all 3 of them listed out or all 2 of them listed out. It's perfectly fine. Well, that is it for today. We have talked about how to factor using the difference of 2 squares, and then how to solve some quadratic equations and some other equations using the difference of 2 squares. I hope that it made sense to you. If you have any questions, I'll see you in class.